somewhere toward the constellations Hercules and Corona Borealis, scattered across a stretch of sky far wider than seems reasonable. A handful of the most violent explosions the universe can produce appear to crowd together. They detonate at nearly the same staggering distance, in nearly the same direction, far more of them packed into one zone than random chance seems willing to allow. And if those explosions are truly mapping something real, a single connected concentration of matter, then it would span a distance so enormous it brushes against the rules we thought the cosmos obeyed at its grandest scales. It might be too large to sit comfortably inside our best picture of reality. So the question becomes almost unbearable. Is that thing really out there? Or is the universe quietly fooling our eyes? Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand what astronomers think they may have stumbled onto out there, you first have to let go of an instinct you have probably carried your whole life. When someone tells you they have found an object in space, you picture a thing. A star you could aim a telescope at. A galaxy you could photograph. A glowing shape sitting against the black, waiting to have its portrait taken. That instinct serves you well for almost everything in astronomy. But the candidate we are circling tonight is different in a way that matters. Nobody has ever taken its picture. Nobody has traced its outline against the sky. There is no single image anywhere of the thing called the Hercules Corona Borealis Great Wall, and there may never be one. What exists instead is a pattern. A faint, argued over arrangement of points on a map, and an enormous claim hanging over those points like a question that refuses to sit down, that they are the fingerprints of something genuinely there. So let us be careful and honest from the very first breath. What we are talking about is not a confirmed, mapped, photographed wall floating in space. It is a proposal, a candidate, a suggestion drawn out of scattered data that some astronomers find compelling and others find unconvincing. And the proposal goes like this. In one direction of the sky, toward the constellations that give the thing its name, there appears to be a region where matter is bunched up more than it has any business being. Not a solid object, not a surface, not a barrier you could ever bump into, but a vast zone of the universe where galaxies and the gas and the dark matter that cradle them may be concentrated more densely than the cosmic average. An overdensity. A lump in the batter, spread across a span so wide that describing it strains the language we normally reach for. And the reason anyone suspects this lump exists at all comes down to one of the strangest detective stories in modern science. Because we did not find the matter directly. We found the explosions. Here is the puzzle the astronomers were actually staring at. Scattered across the deep sky, at tremendous distances, are flashes. Brief, blinding flashes of the highest energy light the cosmos produces. They are called gamma ray bursts, and to understand the rest of this story, you only need to understand a few things about them. The first is that they are, for the few seconds they last, the most luminous events in the entire universe. Nothing else comes close. When one of these bursts goes off, it can briefly outshine everything else in the sky combined, pouring out in a handful of seconds more energy than our own star will release across its entire lifetime of billions of years. Think about what that means for a moment. A single flash, somewhere out in the dark, that for a few heartbeats burns brighter than every star in every galaxy in its neighborhood put together. That is not a metaphor stretched for effect. That is the raw, almost obscene scale of the energy involved. And because they are so violently bright, gamma ray bursts have a remarkable property. They can be seen from absurdly far away. Most things in the universe fade into invisibility once they are distant enough. A galaxy that would blaze in our telescopes if it sat nearby becomes a faint smudge at great distances, and then nothing at all. But a gamma ray burst is so overwhelmingly luminous that we can catch its light even when it has crossed most of the observable universe to reach us. They are like lighthouses so powerful that you can spot them from the far side of an ocean that light itself takes billions of years to cross. And that single fact, that they are visible across almost unimaginable gulfs, is the reason they became useful for hunting something as elusive as a hidden concentration of matter. If you want to map the faraway universe, you need beacons bright enough to be seen out there. Gamma ray bursts are very nearly the brightest beacons that exist. But brightness alone would be useless if the burst went off in random, meaningless places. A flash that has nothing to do with where matter actually sits would tell you nothing about the structure of the cosmos. So, the second thing you need to understand is where these explosions come from, because that is what turns them from mere fireworks into signposts. The long-lasting gamma ray bursts, the kind most relevant here, are thought to mark the death of certain massive stars. When a star far larger than our own runs out of fuel and its core collapses, the result can be a catastrophe so extreme that it blasts out twin jets of energy at very nearly the speed of light. If one of those jets happens to be aimed in our direction, we see a gamma ray burst. The details of that machinery we can leave alone tonight. What matters for the detective story is the kind of star that produces the flash. But not every gamma ray burst is the death of a massive star, and this is a distinction that matters enormously for the detective work, so let us draw it cleanly. When astronomers first began cataloging these explosions, they noticed the bursts came in two flavors, sorted by nothing more complicated than how long they lasted. Some bursts were over almost before they began, flaring and dying in well under 2 seconds, a violent blink, and then nothing. Others lingered, burning for many seconds, sometimes for minutes, a prolonged scream of high energy light. And it turned out this simple split in duration was not cosmetic. The two kinds come from two completely different catastrophes. The short bursts, the quick ones, are now thought to come mostly from the collision of two ultra-dense stellar corpses, neutron stars spiraling together and merging in a final cataclysm. Those collisions can happen almost anywhere, in old quiet galaxies as easily as young busy ones, long after star formation has ended, because the dead stars can drift for ages before they finally meet. So the short bursts are scattered, unmoored from the nurseries, and they make poor signposts for where stars are actively being born. It is the long bursts that carry the story. The long bursts, the lingering ones, are the death cries of the giant stars, the collapse of a single massive sun far heavier than our own. These are the explosions that mark the deaths of the cosmos's most massive stars, and so these are the bursts that can serve as genuine signposts, for reasons we are about to make plain. So when astronomers build a map of matter from gamma ray bursts, they are leaning above all on the long bursts, the ones tethered to star formation. This is why the distinction is not a footnote. The entire logic of using bursts as tracers depends on using the right kind of burst, the kind that genuinely marks a stellar nursery rather than a chance meeting of two drifting corpses in the dark. Mix the two together carelessly and your map blurs. Separate them properly. Keep the long bursts, and you hold the closest thing the deep universe offers to a flag planted in active, matter-rich regions. There is something else about these long bursts that makes them almost miraculously suited to this work, and it has to do with just how far they can be seen. We said earlier that they are blindingly bright, bright enough to be caught across most of the observable universe. But let us put a real edge on that, because it is genuinely staggering. The most distant gamma ray bursts ever recorded come to us from a time when the universe was only a small fraction of its present age, when light had to travel for more than 13 billion years to reach us. From an era so early that the first generations of galaxies were only just assembling out of the primordial dark. Almost nothing else in the universe can be seen across such a gulf. A galaxy at that distance is, for the most part, hopelessly faint, a smudge at the very limit of our greatest telescopes, if it can be seen at all. But a long gamma ray burst at that same distance can briefly blaze brightly enough to be detected without strain. For a few seconds, one dying star outshines the entire faint galaxy that hosts it. And so it carries word of that galaxy's existence across a span of space and time that would swallow almost any other beacon whole. Notice what this gives the mapmaker. The bursts do not just reach far, they reach into the early universe, the young and violent era when star formation across the cosmos was running at its furious peak, when galaxies were forging new stars far faster than they do today. That is exactly the epoch where massive stars were most abundant, and where long bursts would have gone off most frequently. So the bursts are not merely visible at great distances. They are most plentiful, most informative, precisely in the deep past that is otherwise hardest to study. The candidate we are tracing sits at a distance that places it firmly in that fertile, burst-rich era, 10 billion years back, when the universe was busily lit with the deaths of giant stars. The bursts are, in a real sense, beacons tuned to shine brightest in the very age and the very depths where we most need light and have the least. Because massive stars are not scattered evenly through the universe. They cannot be. They burn through their enormous fuel reserves so quickly, in just a few million years, a cosmic blink, that they never have time to wander far from where they were born. A massive star lives fast, dies young, and dies close to its cradle. And where are stars born? They are born in galaxies, in the dense, cold clouds of gas where new stars ignite. They are born in regions of active star formation, the busy nurseries of the cosmos where matter has gathered thickly enough to collapse and catch fire. So follow the logic, because it is the entire foundation of the claim. A long gamma ray burst marks the death of a massive star. A massive star marks a place where stars were recently forming. A place where stars form marks a galaxy rich in gas. And galaxies rich in gas mark the places where normal matter has clumped together. Which means that every time one of these bursts goes off and we catch its light, we have, in effect, planted a tiny flag in a distant galaxy and shouted, there is matter here. There is structure here. The explosion is not the structure. The explosion is a signal flare fired up from inside the structure, telling us the structure exists. That is the beautiful, slightly mad idea at the heart of all of this. You cannot see the faraway scaffolding of the universe directly because it is too faint and too distant. But you can see the brilliant deaths of its stars. And if you collect enough of those deaths and mark where each one happened, you start to sketch, in rough and trembling strokes, where the matter that made those stars must lie. The bursts become a connect the dots picture of the cosmic web, drawn not by us but by the universe lighting its own beacons, one catastrophe at a time. Now, here is where the actual discovery enters. In the year 2014, a small team of researchers, led by the astronomers Istvan Horvath, Jon Hakila, and Zsolt Bagoli, set out to do exactly this kind of map making. They gathered the gamma ray bursts for which astronomers had managed to measure not just a position in the sky, but also a distance. And they began to look at how those bursts were spread out. The expectation, the boring and comfortable expectation, was that the burst should be sprinkled fairly evenly. Not perfectly, of course. The real universe is lumpy on small scales, full of clusters and voids. But once you zoom out far enough and look at the whole sky across enormous distances, the bursts were supposed to smooth into something roughly uniform, a fine and even dusting with no single region hogging more than its fair share. That smoothness is what almost everyone assumed they would find. That is not what they found. In one particular slice of the universe, at one particular range of distances, in one particular patch of sky toward the constellations Hercules and Corona Borealis, there were simply too many bursts. The explosions were crowding together. Far more of them were packed into that zone than an even sprinkling could comfortably explain. It was as if you had expected a scattering of fireflies across a vast dark field to spread into a thin and even glow, and instead watch them gather thickly into one small stretch of the dark while the rest of the field stayed nearly bare. And the team's reaction was the reaction any good scientist has to a pile-up like that. If the explosions are bunched here, then maybe the matter that made them is bunched here too. Maybe these bursts are all flags planted in the same colossal concentration of galaxies. Maybe we are looking at a single, staggering overdensity, a structure larger than anything anyone had dared to name. The distance that this clustering pointed to is worth pausing on, because it tells you not just where the candidate sits, but when. The bursts in question cluster at what astronomers call a redshift of roughly 2. And for now, you only need the plain meaning of that, with the deeper machinery saved for a little later. A redshift of about 2 means the light from these explosions has been traveling toward us for something on the order of 10 billion years. 10 billion years. The universe itself is only about 13.8 billion years old. So this light set out when the cosmos was young, when the Earth and the Sun didn't exist and would not exist for billions of years yet, when the universe was a rougher, brighter, more violent place, busily forging stars at a furious rate. We are not seeing this region as it is today. We are seeing it as it was in deep antiquity, a snapshot from the toddler years of the universe, carried to us across a span of time so long that our entire planet formed, cooled, grew oceans, and sprouted life while that light was still in transit. When we look toward this candidate, we are looking down a tunnel into the ancient past. The name itself, by the way, arrived almost by accident, and it carries a small confession inside it. The structure was not christened in some solemn committee of astronomers. According to the story that has followed it ever since, the label Hercules Corona Borealis Great Wall was coined by a teenager, a young space enthusiast in the Philippines, who put the name onto an online encyclopedia entry. And it simply stuck. There is something fitting about that. An object too big and too uncertain to fully grasp, handed its name by a curious kid on the internet. But the name also misleads, and it is worth flagging that now so it does not quietly distort your picture for the rest of this journey. The word wall conjures a flat, solid, upright thing, a barrier with two sides. This candidate is almost certainly nothing of the kind. To the extent it exists at all, it appears to be more of a sprawling, roundish, blobby region than a thin standing sheet, and it is in no sense a surface you could touch or run into. It is a statistical lump, a place where the density of matter may run a little higher than average across a tremendous volume. Calling it a wall is a bit like calling a faint thickening of fog a fortress. The drama of the word has helped the structure become famous, but the word is doing the structure a quiet disservice. So that is the shape of the proposal as it first arrived. A region toward Hercules and Corona Borealis, a clustering of the brightest explosions in nature, a distance that places it 10 billion years in the past, and an interpretation, bold and contested, that all those explosions are tracing a single connected concentration of matter so large it would dwarf every other structure astronomers had ever catalogued. If true, it would be the largest known thing in the universe by a wide margin. If true, and that conditional is not a throwaway. It is the entire reason this is a story worth telling slowly, because almost everything about it lives in the gap between the data we trust and the interpretation we are not sure we can. Which brings us to the crack running through the whole foundation, the flaw you must hold in mind from here forward, because it is the seed from which every doubt in this story grows. Gamma ray bursts, for all their blinding usefulness, are terrible tracers in one specific and unavoidable way. They are rare, staggeringly, frustratingly rare. Across the whole sky, in any given year, only a modest number of these bursts are detected at all, and of those, only a fraction have their distances successfully measured. Measuring the distance is the hard part. You have to catch the burst quickly, point other telescopes at its fading afterglow before it vanishes, and tease out the redshift from that dying light, all in a race against the clock. The result is that when you assemble every well-measured burst humanity has ever recorded across all of cosmic history, you're not working with millions of data points, or even tens of thousands. You are working with a few hundred flags to map a universe that is tens of billions of light years across in every direction and billions of years deep in time. Sit with how thin that really is. Imagine mapping every forest on an entire planet, but your only tool is a record of where, over many years, a handful of lightning strikes happen to start fires. Lightning does tend to strike where there is something to burn. So the fires are not random, they do carry real information about where the forests are. But there are so few of them, spread so thinly across such an immense area, that any map you draw will be full of gaps and guesses. You will have whole continents marked by a single scorch mark, or by none at all. And crucially, if a few of those rare fires happen to land near one another just by chance, you might be tempted to circle that cluster and announce a great forest, when in truth you had simply caught a run of unrelated sparks. The sparseness does not just make the map blurry, it makes it dangerously easy to see shapes that are not there. That is the tension that will drive everything still to come. The gamma ray bursts are real. The clustering toward Hercules and Corona Borealis, as it appears in the data, is something astronomers have measured and remeasured. Those are facts. But the leap from a clustering of a few hundred rare flashes to the confident declaration of a single connected structure 10 billion light years wide is exactly the kind of leap that sparse data makes treacherous. Maybe the bursts really are flags in one titanic overdensity, the largest thing the universe has ever built, Or maybe they are a handful of unrelated sparks that, by the cruel arithmetic of chance and the quirks of how we collect them, only look like they belong together. The whole controversy lives in that maybe. And notice what the astronomers themselves did, because it tells you they were not naive about this. They could simply have eyeballed the clustering and called it a day. Instead, the discovery rested on the claim that the pileup was too strong to be a fluke, that the odds of so many bursts crowding into that zone purely by accident were small enough to take seriously. That is the right question to ask of a sparse dataset. And it is a question we will return to with real teeth, because not everyone agrees on the answer. But for now, the important thing is simply to feel the structure of the problem clearly. We have brilliant, trustworthy beacons. We have far too few of them. And we have a pattern that may be a glimpse of the grandest architecture in existence. Or maybe the universe arranging its scarce sparks into a face we only imagine we recognize. There is one more thread to lay down before we move on, because it sharpens why the bursts, even as beacons, are imperfect signposts in a subtler way. A gamma ray burst does not mark all of the matter in a region. It marks star formation, specifically the births and rapid deaths of massive stars. So a burst is biased toward galaxies that were busily making stars at that moment in cosmic history. Regions full of quiet, settled galaxies that had finished their star-forming youth would fire off few bursts or none, even if they were dense with matter. And regions blazing with new star formation would light up with bursts out of proportion to how much total matter they held. So, the connect the dots picture the burst draw is not a faithful map of all matter. It is a map weighted toward where stars were actively being born. A real concentration of galaxies might show up brilliantly, or it might be underrepresented, depending on what its galaxies were doing when their light set out. It tells a true story, but a deeply selective one, shouted only by the loudest, most violently star-forming corners of the deep past, while quieter regions, however rich, stay nearly dark. And the selectiveness runs deeper still, in a way that should make any honest mapmaker uneasy. It is not only that bursts favor regions making stars, it is that among star-forming regions, they appear to play favorites in a subtler way, one tied to the chemistry of the galaxies they go off in. The earliest stars in the universe form from almost pure hydrogen and helium, the simple ingredients left over from the birth of everything. Only later, as generations of stars lived and died, did they forge the heavier elements, the carbon and oxygen and iron, and scatter them into the gas, slowly enriching it. Astronomers call the abundance of those heavier elements a galaxy's metal content, and there is mounting evidence that long gamma-ray bursts prefer galaxies that are poor in those metals, the more primitive, less chemically enriched systems. The exact reasons are still argued, tangled up in how the most massive stars collapse, but the upshot for our purposes is plain and troubling. If bursts favor metal-poor galaxies, then they do not even faithfully trace all-star formation. They overreport the chemically young, primitive corners of the cosmos, and underreport the richer, more evolved ones, even when both are busily forming stars. Stack these biases on top of one another, and feel how filtered the burst map really is. A gamma ray burst marks not all matter, but star formation. And not all star formation, but massive star formation. And among that, it leans toward the metal poor and the chemically primitive. Each filter is a tilt, a thumb on the scale, a way in which the bursts shout loudly about some regions and stay nearly silent about others that may hold just as much matter or more. So, when those flags cluster toward Hercules and Corona Borealis, we have to ask not only whether the clustering is real, but whether it traces a genuine concentration of matter or merely a concentration of the particular kind of galaxy that bursts happen to favor. A region rich in primitive, vigorously star forming galaxies would light up with bursts whether or not it held more total matter than its neighbors. The tracer is not just sparse and not just selective, it is selective in layered, compounding ways. And every layer is one more reason to doubt that a pileup of flags marks one titanic concentration of matter, rather than the few galaxies that happen to shout loudest. Hold all of that together, and you have the honest opening picture. Out toward Hercules and Corona Borealis, 10 billion years back in time, the brightest explosions the universe can make appear to cluster more tightly than chance seems to allow. From that clustering, astronomers proposed a single colossal concentration of matter, named it a Great Wall, and floated the possibility that it is the largest structure ever found. The explosions are real and the pattern is measured, but the explosions are rare and selective tracers, and the leap to one connected object is exactly where reasonable scientists begin to part ways. We have not yet asked how you turn a scatter of flashes into a measured size, or why a structure this large would unsettle our deepest assumptions about the cosmos, or whether the whole thing might dissolve under scrutiny into chance and bias. Those questions are coming, each in its turn, but they all grow from this single soil. A handful of distant beacons, a suggestive pileup, and the oldest temptation in science, which is to look at a few scattered points and insist that you can see the shape they belong to. So now we arrive at the question that should be nagging at you. If nobody has ever photographed this thing, if all anyone has is a scatter of distant flashes, then how on earth does a number like 10 billion light years even get attached to it? Where does a size come from when you cannot see the object whose size you are measuring? This is not a trivial question, and the answer is where a great deal of the doubt in the story quietly lives. Because turning a handful of points of light into a three-dimensional structure with a measurable width is not a simple act of reading a ruler. It is a tower of inference, each layer resting on the one below, and the size you get at the top depends enormously on the assumptions you stacked along the way. To understand why the dimensions of this candidate are argued over, you first have to understand how those dimensions are built at all. Start with the most basic problem in all of astronomy. When you look up at the sky, everything appears to sit at the same distance. The sky is a dome, a flat ceiling with light stuck to it. A nearby star and a galaxy a billion light years behind it can sit side by side in your field of view, looking for all the world like neighbors, when, in truth, one is unimaginably farther away than the other. The sky gives you two numbers for free and withholds the one that matters most. It tells you direction, where on the dome a thing sits, up and over and across, but it refuses to tell you depth. It will not tell you how far away anything is. And without depth, you cannot have structure. A clustering of explosions that looks tight and meaningful on the flat dome of the sky might, in reality, be a scattering of unrelated flashes strung out across billions of light years of depth, lined up by pure coincidence from our particular vantage point, like streetlights in a photograph that seem to touch but stand miles apart. Direction alone is a shadow. To find a real structure, You need the missing dimension. You need distance. And here is where redshift enters, the single most important tool in this entire story. The thing that turns a flat smear of dots into a map with genuine depth. The idea behind it is one of the most beautiful in science, and you can grasp it without any mathematics. The universe is expanding. Space itself is stretching, carrying everything in it apart, and it has been doing this for billions of years. Now think about what that stretching does to a beam of light crossing that space. Light is a wave, and the color of light is set by the length of its waves, with bluer light having shorter waves and redder light having longer ones. When a gamma ray burst, or the galaxy around it, sends light toward us across an expanding universe, that light has to travel for an enormous span of time, and the whole way, space is stretching beneath it. The light waves get stretched right along with the space they are moving through. They get longer. They slide toward the red end of the spectrum. By the time that light reaches us, its waves are longer than they were when they left. And the amount of that stretching is what we call redshift. The deep elegance is this. The longer the light has been traveling, the more space has stretched beneath it, and so the more its waves have been pulled out. A small redshift means light that has not traveled far from something relatively nearby that we see almost as it is now. A large redshift means light that has crossed a vast gulf of space and time, stretched dramatically along the way from something far away that we see as it was long ago. So, redshift is not just a measure of distance, it is a measure of distance and time fused into a single number. Because in an expanding universe, to look far is to look back. When astronomers say the bursts in this candidate cluster at a redshift of roughly 2, they mean the light has been stretched by a specific measurable amount, and that amount corresponds to light that set out around 10 billion years ago, from a part of the universe now extraordinarily far from us. Redshift is the yardstick. It is how you recover the depth the flat sky tried to hide. Now put the two coordinates together and feel what just happened. For each gamma ray burst, you have its direction on the sky, the two numbers the dome gives you for free. And now, through redshift, you have its distance, the third number, the depth, 2 plus 1. With all three, each burst is no longer a dot pinned to a flat ceiling. It becomes a point floating in three-dimensional space, a real location in the cosmos. And once every burst has a genuine position in 3 dimensions, you can finally ask the question that matters. Do these points actually cluster in space, packed close together in all 3 dimensions at once? Or do they only appear to cluster on the flat sky while in truth, they are strewn across wildly different depths? A false huddle dissolved the moment you add the third dimension. Redshift is what lets you tell those two cases apart. It is the difference between a structure and a mirage. But here is the first crack, and it is a serious one. Measuring a redshift is hard, and for gamma ray bursts it is brutally hard. Remember what these things are. They are flashes. They blaze for seconds and then begin to die, their afterglow fading by the hour. To capture a redshift, astronomers have to scramble. The moment a burst is detected, they must whip other telescopes around to catch the fading light and pull the redshift out of it before it slips away forever. This race is lost far more often than it is won. The result is that of all the gamma ray bursts ever detected, only a minority have a measured distance at all. The rest are points on the flat dome with no depth, useless for building a 3-dimensional map. So the already sparse population of burst gets thinned even further, down to those precious few hundred for which we know both where and how far. Every layer of this story keeps shrinking the dataset, and a map drawn from a few hundred points spread across the entire observable universe is a map made mostly of empty space and assumption. So, picture honesty, what the astronomers are actually working with when they sit down to find this structure. Not a glowing wall, not even a dense field of dots. A scattering of a few hundred points, floating in a colossal three-dimensional volume, most of them nowhere near each other, and somewhere in that thin haze, in one region and at one depth, a place where the points seem to crowd a little more tightly than elsewhere. The structure, if it is a structure, is not something you see. It is something you detect, a faint statistical thickening in a sparse cloud. And now comes the truly delicate step, the one that produces the famous number. How do you take that faint thickening and assign it a size? This is where method becomes everything, and where the dimensions of this candidate stop being a fact and start being a result, a thing that depends on the choices of the person measuring it. To estimate how big the clustering is, astronomers have to draw a boundary around it. They have to decide which bursts belong to the structure and which are just background, foreground, neighbors that happen to lie nearby but are not part of the lump. And there is no glowing edge to guide them, no surface where the structure obviously stops. The overdensity, if it exists, fades gradually into the ordinary scatter around it, the way a thicker patch of fog has no clean border, but simply thins out until you cannot say where it ended. So the astronomers must impose a rule. They must choose how close together points have to be to count as clustered, how far out to extend the membership, how to weigh the thin gaps between the flags. And every one of those choices nudges the answer. Draw the boundary generously, and the structure swells. Draw it tightly, and it shrinks. Decide that a distant pair of bursts at the edge belongs to the same family, and you have just stretched the wall by another billion light years. Decide they are outsiders, and you have trimmed it. This is why you will hear the size of this candidate quoted in ranges rather than as a single crisp figure, and why those ranges shift from study to study. The often repeated headline is that it spans something like 10 billion light years, which corresponds in the units astronomers prefer to a scale of roughly 2 to 3,000 megaparsecs, or 2 to 3 gigaparsecs. But that figure is not read off an instrument. It is the output of a statistical procedure applied to a sparse set of points, and a different procedure or different assumptions about which bursts belong can move it substantially. Later analyses using larger burst catalogs have even suggested the clustering may sprawl across a wider range of distances than the original work proposed, hinting the candidate could be larger still, or that it may be several overlapping concentrations rather than one clean object. The point is not that any of these numbers is dishonest. The point is that the size is inseparable from the method that produced it. When something has no visible edge, its measured dimensions will always carry the fingerprints of the people doing the measuring. This is not a flaw unique to this candidate. It is the unavoidable nature of measuring a faint pattern in thin data, and it is precisely why honest scientists keep arguing about how big the thing is, or whether the thing is one thing at all. Now, before we go any further, we have to kill a misunderstanding that the name has been quietly planting in your mind this whole time, because if we let it stand, it will warp everything that follows. The word is wall, and a wall, in every ordinary sense, is a barrier. It is solid, It is flat. It has two faces and an edge. It is the kind of thing that stops you, that you could press your hand against. Whatever this candidate is, it is none of those things, and the gap between the word and the reality could not be wider. There is no surface here. There is no solid sheet of anything. You could fly through the entire region for 10 billion light years and never once strike a barrier, never feel a wall, never encounter anything but the same near perfect emptiness that fills the rest of space, punctuated here and there by a galaxy. The thing is not dense in any human sense of the word. It is not even dense in any planetary or stellar sense. It is dense only in the faintest statistical whisper, meaning that across an unfathomable volume, the galaxies may be packed very slightly closer than the cosmic average. A little more than usual, spread across a little under forever. Let that recalibrate your image entirely. When you hear Great Wall, do not picture a rampart standing in the dark. Picture instead an almost imperceptible thickening in a mist that fills all of space. A region where the scattered galaxies lean fractionally toward one another, detectable only because you can stand far enough back and count beacons and notice that one zone holds a few more than its share. The matter is still overwhelmingly empty space. The structure, if real, is a tendency, a bias, a gentle overpopulation, not an object with walls. And to make the misnomer worse, the early analysis suggested the region is not even shaped like a wall. A wall should be thin and flat and elongated, a sheet. This candidate appears to be more rounded, more blobby, more like a vast swollen region than a standing partition, which has led some to remark that if it is anything, it is more like an enormous supercluster than a wall at all. The name is a piece of poetry that stuck. It is not a description. Hold on to that because the size we have been discussing is the size of a faint statistical lump, not the size of any solid thing. And that distinction will matter enormously when we ask whether such a structure should be possible. But sizes mean nothing without something to compare them against. Let us build a ladder, rung by rung, from the structures we know are real, up toward the scales this candidate claims to occupy. Because the bare phrase, 10 billion light years, cannot be felt. It is just words. The feeling only comes when you climb to it from below and watch each familiar giant shrink to nothing beneath you. Begin at a rung you can almost hold in your mind. A galaxy. Our own Milky Way is about 100,000 light years across, a flat spiral of a few 100 billion stars. It is so large that light, the fastest thing in existence, needs 100,000 years just to cross from one edge to the other. By any human standard, a galaxy is the very definition of immense. Every star you have ever seen with your naked eye lives inside this one structure. Plant that as the bottom rung, 100,000 light years. Hold it. Now climb. Galaxies are not solitary. They gather into groups and clusters, gravitationally bound families of dozens, hundreds, sometimes thousands of galaxies orbiting a shared center. A large galaxy cluster might span 10 or 20 million light years from side to side. So, in one step up the ladder, we have leapt from 100,000 to perhaps 20 million, a couple hundred times larger. The Milky Way, that unimaginable spiral, is now just one member of a swarm, and the swarm is 200 times wider than the spiral. Already the ground is falling away beneath us. Climb again. Clusters themselves gather into superclusters, sprawling assemblies of many clusters strung together. Our own home supercluster, the vast structure our galaxy belongs to, has been mapped as a flowing region called Laniakea, a Hawaiian name meaning immeasurable heaven, and it stretches across something like 500 million light years, from 20 million to 500 million. Another enormous leap. Our entire cluster of galaxies is now a small knot inside a structure 25 times larger, and the Milky Way within it has become a single point of dust. 500 million light years, and we are still nowhere near the top. Climb once more to the largest structures astronomers have confidently catalogued, the genuine cosmic walls and filaments that thread the universe. The most famous of these, the Sloan Great Wall, discovered by mapping the three-dimensional positions of vast numbers of galaxies, stretches across something like 1.33 billion light years. Now we have crossed the billion mark. This is a real, well-studied structure, a true wall of galaxies, and it is more than 10,000 times wider than our entire galaxy and far larger than our home supercluster. The Sloan Great Wall is, by most reckonings, one of the largest things in the universe whose existence is widely accepted. Stand on this rung and look down, and the Milky Way is no longer even visible. It is less than a grain of dust on a structure that runs for well over 1 billion light years. And now, only now, do we reach for the candidate at the top. And only now can you feel what its claimed size actually means. The Hercules Corona Borealis Great Wall, if the interpretation holds, would span on the order of 10 billion light years. Set that against the rung we just stood on. The Sloan Great Wall, that confidently accepted giant, runs about 1.33 billion. This candidate would be something like 7 or 8 times larger than that. It would dwarf the largest structure most astronomers accept as real. Stack the Sloan Great Wall end to end 7 times, and you would only just begin to span it. And compared to where we started, compared to a 100,000 light year galaxy, the candidate would be 100,000 times wider. 100,000 Milky Ways laid in a line, edge to edge, would be needed just to cross it once. But here is the comparison that truly stops the breath. The one that tells you why this candidate is not merely large, but disturbingly large. The observable universe itself, the entire sphere of everything we could ever in principle see, stretches about 93 billion light years from one side to the other. A structure 10 billion light years across would therefore span a meaningful fraction of the whole observable universe, something like 1/10 of everything we can see, laid across by a single connected pattern. And here is something that should sharpen your unease rather than soothe it. This candidate is not alone in its strangeness. It is not a single freak result standing isolated against an otherwise tidy cosmos. Over the past couple of decades, astronomers hunting through the deep universe have turned up a small rogues gallery of candidate structures, each one straining against the same expectations, each one discovered by similar detective work on sparse and distant beacons. And placing our candidate among its siblings tells you something important. Either the deep universe is genuinely lumpier on enormous scales than the simplest picture allows, or there is some recurring trap in how we hunt for structure that keeps producing the same kind of giant phantom. Both possibilities are unsettling, and both are live. Consider one of these siblings, found by mapping not explosions but quasars, the blazing cores of galaxies where matter spirals into supermassive black holes and shines across the cosmos. In the year 2013, astronomers reported a vast grouping of these quasars, dozens of them, strung together across a span of roughly 4 billion light years. They called it the Huge Large Quasar Group, and 4 billion light years is by any measure an absurd distance for a single connected grouping. It comfortably exceeds the scale at which structure was supposed to smooth away, and it sits in the same uncomfortable territory as our candidate. A clustering of bright distant beacons that may or may not trace one coherent thing. It is smaller than the Hercules Corona Borealis candidate, but it is built from a completely different kind of beacon, and that is precisely what makes it interesting. Two different tracers, quasars and bursts, both seeming to reveal structures larger than the rules permit. Then there is a stranger sibling still, and this one comes back to gamma ray bursts, though arranged in a shape no one expected. A team studying burst positions reported a configuration in which 9 of these explosions, all at a similar distance, appeared to fall along the outline of an enormous ring on the sky, a near circular arrangement spanning something like 5 billion light years across. They called it the Giant Gamma Ray Burst Ring, and the very shape of it, a ring, deepened the puzzle because it is hard to imagine what physical structure would arrange matter into so vast and so regular a loop. Was it a real ring of matter? Some unimagined feature of the deep cosmos? Or was it exactly the kind of striking shape that sparse data and an eager eye conspire to produce? A circle conjured purely out of chance, the way scattered points can fall by accident into a loop the mind insists is real. Notice the thread running through all of these. The Sloan Great Wall, accepted and real, mapped from countless galaxies. The Huge Large Quasar Group, contested, mapped from quasars. The Giant Gamma Ray Burst Ring, contested, mapped from bursts. And our candidate, the largest and most contested of them all, mapped from bursts as well. They form a kind of spectrum, running from the solidly confirmed to the deeply doubtful, and they are not independent curiosities so much as repeated knocks on the same door. Each one asks the same question in a slightly different voice. How big is the universe truly allowed to let its structures grow before the rules say enough? And each one, in its own way, hints that the answer our simplest models give, a few 100 million light years and no more, might be too small. Our candidate sits at the far, wild end of this spectrum. The largest claim, the thinnest data, the loudest controversy. But it does not stand alone out there. It stands at the end of a line of strange siblings, all of them gesturing toward the possibility that the grandest scales of the cosmos hold more architecture than we were prepared to find, and all of them haunted equally by the possibility that the architecture is a trick of the sparse and distant light we are forced to read it by. Think about what that demands. We are not talking about a large object inside the cosmos. We are talking about something so large that it would constitute a substantial slice of the cosmos itself. A feature you could not fit many copies of into all of visible reality. Most things in the universe, however vast, are still small enough that the universe holds countless copies of them. There are 2 trillion galaxies. There are uncountable clusters. But a structure this size would be nearly unique by sheer necessity, because the observable universe could only contain a handful of objects this large at all. It is not a star in the cosmic ocean. It is a continent stretched across an appreciable portion of the entire sea. And that is exactly where the unease begins to gather, though we will not yet let it loose. Climb back down the ladder in your mind and notice the pattern you just traversed. At each rung, structures gathered into larger structures, and that gathering felt natural. because gravity pulls matter together over time, and the universe has had billions of years to do the pulling. Galaxies into clusters, clusters into superclusters, superclusters into walls and filaments. Each step made sense. But the steps were taking time, vast amounts of time, because gravity works slowly, and the larger the structure, the longer it should take to assemble. And here, at the top of the ladder, sits something so large that you begin to wonder whether the universe has even existed long enough to build it. Whether there has been time since the beginning of everything for gravity to gather matter across a span of 10 billion light years into a single connected whole. That question, the question of whether this thing is not just big but impossibly big, too big for the age and the rules of the cosmos to allow, is the door we are standing in front of now. We have done what this stretch of the journey needed to do. We have seen how the flat, depthless sky withholds the one dimension that structure requires, and how redshift, by reading the stretch that an expanding universe imprints on traveling light, hands that missing depth back, turning a smear of flashes into points floating in real three-dimensional space. We have seen how brutally hard those distances are to measure for objects as fleeting as gamma ray bursts, and how the dataset keeps thinning at every step until only a few hundred well-placed beacons remain. We have seen that the famous size is not read from an instrument but built by a method, drawn by choosing where a borderless lump begins and ends, which is why the number floats and the experts argue. We have stripped the word wall of its false solidity and replaced it with the truer image of a faint statistical thickening in an almost perfectly empty mist, rounder than a wall and denser only in the gentlest whisper. And we have climbed the ladder of cosmic scale from our galaxy up through clusters and superclusters and the accepted Great Walls, until we reached a candidate so large it would span a tenth of all we can see. What we have not yet asked is why a structure of this size should trouble anyone at all. Why its mere existence, if it is real, pushes against something the entire edifice of modern cosmology was built to assume. That assumption has a name and a logic and a reason it has held for a century. And it is what we turn to next. There is a quiet assumption sitting underneath nearly everything astronomers believe about the universe, and you have probably never been told it outright, because it hides so well that even the people who rely on it sometimes forget. It is a choice. It is the assumption that we are not special, not specially located, not sitting in some privileged spot from which the cosmos looks different than it would from anywhere else. The assumption is that if you could be teleported to some random galaxy 10 billion light years away and look around, you would see, in the broad strokes, the same kind of universe you see from here. The same scattering of galaxies, the same web of clusters and voids, the same overall texture in every direction. Not identical in detail, of course. No two patches of sky are ever exactly the same, but statistically the same. The same on average. The same once you blur your eyes and stop counting individual galaxies and start measuring the universe by the bucketful. This assumption has a name. It is called the cosmological principle, and it is one of the load-bearing walls of modern cosmology. And the candidate we have been tracing all this time threatens, if it is real, to put a crack in it. Let us build the principle up slowly, because it is more profound than it first sounds, and because the entire tension of this story is impossible to feel until you understand what would actually be at stake. The cosmological principle rests on two ideas that sound similar but are subtly different, and you need both. The first is homogeneity. Homogeneity means that the universe is, on large enough scales, the same everywhere. Pick any large region anywhere in the cosmos, and it will contain roughly the same amount of matter, roughly the same number of galaxies, roughly the same density as any other large region you might pick. No place is fundamentally richer or emptier than any other once you zoom out far enough. The universe has no center, no special dense heartland, no privileged barren edge. It is in the large, evenly filled. The second idea is isotropy. Isotropy means that the universe looks the same in every direction. Stand anywhere and turn slowly in a circle, looking out into the deep cosmos. And no matter which way you face, the view is statistically the same. There is no special direction, no axis the universe is built around, no way to point and say, that way lies the busy part of the cosmos, and that way lies the quiet part. Every direction is, on average, equivalent. Homogeneity says every place is the same. Isotropy says every direction is the same. Together they form the cosmological principle, the claim that the universe, viewed at sufficient scale, is smooth and featureless and democratic, granting no location and no orientation any special status. Now you might immediately object, and you would be right to, that this is plainly false on the scales we actually live in. Look around. The universe is not smooth at all. It is violently lumpy. Here's a planet. There is empty space. Here is a blazing star. There is a cold void. Here is a galaxy crammed with hundreds of billions of suns, and around it, enormous gulfs of nearly perfect emptiness. Zoom out further, and the lumpiness does not vanish. It organizes. Galaxies clump into clusters. Clusters string into superclusters. Superclusters thread into vast filaments and walls, with cavernous voids yawning between them, regions hundreds of millions of light years across where almost nothing lives. The universe, on every scale we have so far climbed in this story, looks like anything but a smooth and even soup. It looks like a wild, tangled, frothing web. So, how can anyone seriously claim the universe is homogeneous and isotropic when the evidence of our own eyes screams that it is clumpy beyond belief? The answer is the single most important idea in this part of the story, and it is the hinge on which the entire tension turns. The cosmological principle does not claim the universe is smooth on small scales. It claims the universe becomes smooth when you zoom out far enough. There is supposed to be a scale, a specific size, beyond which all the clumpiness washes out and the universe finally settles into its democratic evenness. Below that scale, lumps and voids and walls dominate everything. Above it, they vanish into uniformity. Think of a sandy beach. Crouch down and press your eye to the sand, and it is anything but uniform. It is a chaos of individual grains. Here a pebble, there a gap, here a shell, a wild and lumpy landscape. But stand up and look down the length of the beach, and all of that grain by grain chaos blurs into a single, smooth tan surface. The lumpiness did not disappear. You simply zoomed out past the scale at which it mattered, and at the larger scale, the beach is uniform. The cosmological principle says the universe is exactly like this. Lumpy when you look closely, smooth when you stand back, with a particular height at which standing up converts the one into the other. And here is the crucial part, the number that everything hinges on. Cosmologists have estimated, from theory and from observation, roughly where that transition should happen. The scale at which the universe is expected to finally smooth out, the so-called scale of homogeneity, is thought to lie somewhere in the neighborhood of a few 100 million light years. Below that, you find clusters and superclusters and walls, the rich, tangled architecture. But once you start examining the universe in chunks larger than a few 100 million light years across, the clumps are supposed to average away. Take any two enormous boxes of space, each 1 billion light years on a side, from opposite ends of the cosmos, and they should contain essentially the same amount of matter. The walls and voids inside each box are real, but they are small compared to the box, so they blur into the same smooth average. That is the promise of the cosmological principle. Past a few 100 million light years, the universe runs out of structure. Nothing should be bigger than that. There should be no feature, no clump, no concentration that holds together as a single coherent thing across scales much larger than that ceiling. Now you can feel the collision coming. Hold that ceiling in your mind. A few 100 million light years. The scale past which the universe is supposed to surrender all its lumpiness and become smooth. And now recall the candidate we spent so long climbing toward. The Hercules Corona Borealis Great Wall, if the interpretation of those clustered explosions holds, would span something on the order of 10 billion light years. Set the two numbers side by side and the problem leaps out. The candidate is not slightly larger than the scale of homogeneity. It is not twice as large or 5 times as large. It is something like 20 or 30 times larger than the scale at which the universe was supposed to have run out of structure entirely. It is a coherent feature sprawling across a span where, by the logic of the cosmological principle, there should be no coherent features at all. Where the universe should be a smooth and democratic average, this candidate would be a single connected concentration, a lump persisting at a scale far beyond where all lumps were meant to dissolve. This is what people mean in the careful version when they say the structure might be too big to exist. They do not mean it is physically impossible for matter to occupy that much space. Obviously, the observable universe is far larger still. They mean something more specific and more unsettling. They mean that a single coherent overdensity of that size strains against the scale of homogeneity, against the expectation that nothing should hold together as one structure past a few 100 million light years. The candidate, if genuine, would be a clump existing where the rules said clumps cannot, a feature persisting at a scale where the universe was supposed to have gone featureless. That is the tension. That is why a clustering of gamma ray burst toward Hercules and Corona Borealis is not merely a curiosity but a potential challenge to one of the deepest assumptions in all of cosmology. And there is a second blade to the problem, sharper even than the first, which is the matter of time. We touched on it at the very top of the ladder, and now we can press on it properly. Structures in the universe are built by gravity, and gravity is patient but slow. In the beginning, just after the universe was born, matter was spread almost perfectly evenly, with only the faintest whispers of unevenness. Regions a hair denser than their surroundings, by only about a part in 100,000. Over billions of years, gravity went to work on those whispers. The slightly denser regions pulled in a little more matter, which made them denser still, which let them pull harder. In a slow, snowballing collapse, galaxies formed, then groups, then clusters. Then, given enough time, the clusters were drawn into superclusters and wars. But every step in that hierarchy takes time, and the larger the structure, the longer it takes, because gravity must coordinate matter across a greater and greater distance, and gravity cannot work faster than the universe allows. To assemble a coherent structure 10 billion light years across, gravity would need to have drawn matter together across that entire span. And the universe is only about 13.8 billion years old. There may simply not have been enough time since the very beginning of everything for gravity to gather matter into a single connected structure that large. The candidate would be not only too big for the scale of homogeneity, but potentially too big for the age of the cosmos, a structure that the universe has not lived long enough to build. It is worth unfolding that argument slowly, because the slowness is more profound than the bare claim suggests, and it rests on a limit even gravity itself cannot break. Gravity does not act instantly across distance. Like everything else in the universe, its influence cannot travel faster than light, which means that to gather scattered matter into one coordinated structure, gravity must in effect reach across the entire span of that structure and draw its far-flung parts into concert with one another. For a galaxy's worth of matter, the span to be bridged is modest, the reaching is swift, and the structure pulls itself together and ignites comfortably within the lifetime of the cosmos. The distance to be coordinated is small, and so the time required is small. Hold that link between distance and time clearly, because everything now turns on it. And you can see the proof of this limit written into the universe right now, if you know where to look for it. The very largest things we observe today, the great superclusters and the accepted cosmic walls, are not finished. They are not settled, gravitationally bound, completed objects the way a galaxy is. They are caught in the very act of formation, still drawing themselves inward across spans so enormous that the gathering remains visibly, measurably incomplete, even after billions upon billions of years. This is why astronomers will tell you that the largest fully bound structures in all the cosmos are the galaxy clusters, the swarms of hundreds or thousands of galaxies that have actually finished falling together. Step beyond them to the superclusters and the walls, and you have stepped past the point where gravity has had the time to complete its work at all. Those grander assemblies are real, and they are vast, but they remain loose and unfinished, never yet pulled tight into a single bound whole. But here is the crucial asymmetry. The thing that turns a vague worry about time into a hard ceiling. The larger the structure you wish to build, the longer gravity needs, and not merely in proportion, but punishingly so. To assemble a cluster, gravity must reach across millions of light years and draw matter together over that whole span, and that takes far longer than building a single galaxy. To assemble a supercluster, it must coordinate matter across hundreds of millions of light years, longer still. Each rung up the ladder of size demands a steeply growing investment of time, because gravity must work across a steeply growing distance, gathering ever more matter from ever farther away into a single coordinated whole. Structure builds from the bottom up, small things first, larger things only later, each tier requiring the patient accumulation of the tiers below. The universe assembles its architecture the way a slow mason builds a cathedral, stone upon stone, and the grandest features are necessarily the last and the longest in the making. And now the ceiling reveals itself plainly. The universe is about 13.8 billion years old. That is all the time gravity has ever had, every second since the whisper-faint seeds were laid down. In that span, gravity has had time to build galaxies in abundance, clusters readily, superclusters, and the largest accepted walls only barely, working at the very limit of what the available time allows. Beyond that limit lies a size that gravity simply has not had the time to reach, a scale at which it could not yet have coordinated matter into a single connected structure. Because the universe has not lived long enough for the gathering to finish, this is the second blade of the tension, sharper and more concrete than the first. A coherent structure 10 billion light years across would demand that gravity have built across that entire span. And the arithmetic of cosmic time says there has not been nearly enough of it. The candidate would be not merely lonelier than the rules of smoothness permit, but younger than its own size should allow, a finished cathedral standing in a universe that has only had time to lay foundations. So if you've been waiting for the dramatic conclusion, the moment where the brave clustering of explosions topples the edifice of modern cosmology and rewrites the textbooks, this is exactly where we have to slow down, breathe, and refuse to take the easy and thrilling path. Because the temptation here is enormous, and it is wrong. The temptation is to say that if this structure is real, then the cosmological principle is shattered. The foundations of cosmology are rubble, and everything we thought we knew about the universe falls. That is the version that makes headlines. It is also a serious overstatement, and an honest telling has to push back against it firmly, because the reality is far more measured and far more interesting than the demolition fantasy. Here is the first reason for restraint. The cosmological principle has never been a claim that the universe is perfectly, exactly homogeneous. It has always been a statement about averages and tendencies. The real universe is allowed to have fluctuations, regions that run a little denser or a little emptier than the mean. The question is never whether such fluctuations exist. Of course they do, but how large they're allowed to get and how rare a given size should be. A modestly oversized structure is no crisis at all. Even a surprisingly large one might be a rare statistical excursion, the kind of unlikely but not impossible fluke that any vast random process throws up occasionally if you wait long enough and look at enough sky. The existence of one big structure does not by itself break the principle. It only starts to bite if the structure is so large and so unlikely under the standard picture that you cannot comfortably write it off as a rare fluctuation. And whether this candidate crosses that line is precisely what is in dispute, not a settled fact. The principle does not stand or fall on a single object. It is a statement about the whole statistical character of the cosmos, and you do not overturn a statistical claim with one anecdote. Here is the second reason for restraint, and it is the one most often forgotten in the excitement. Even if the structure were granted to be completely real, exactly as large as claimed, and genuinely a single coherent overdensity, it would still not disprove the Big Bang, and it would still not collapse modern cosmology into nothing. This is a point worth saying slowly and clearly, because the loose talk around this candidate constantly blurs it. The Big Bang model, the expanding universe, the cosmic history we have pieced together from a dozen independent lines of evidence. None of that rests on the cosmological principle being flawless. The principle is a simplifying assumption, an enormously useful one, that makes the equations of cosmology tractable and that fits the data we have astonishingly well on the scales we have tested. But a tension with that simplifying assumption at the very largest scales would not erase the evidence for an expanding universe, would not unsay the cosmic microwave background, would not rewind the abundance of the light elements forged in the first minutes, would not undo any of the pillars on which the Big Bang actually stands. At absolute most, A confirmed structure of this size would mean that our simple assumption of large-scale smoothness needs refining, that the universe is lumpier on the grandest scales than our tidiest models assumed, that the scale of homogeneity sits higher than we thought or behaves in some subtler way. It would be a correction, possibly a deep and important one, to one assumption within cosmology. It would not be the death of cosmology. A crack in one wall is not the fall of the house. And here is the third reason for restraint, the most important of all, and the one that quietly rules everything still to come. For the structure to threaten the cosmological principle, even mildly, it has to be real in the specific sense that matters. It has to be one genuine, connected, coherent overdensity. And that is exactly the part we have not established and have every reason to question. Walk back through everything we have built. The structure is inferred from a few hundred rare, fleeting explosions. Those explosions trace only the busiest star-forming corners of the deep past, not all the matter. Their distances are agonizing to measure, thinning the dataset further. The size is not read from an instrument but constructed by a method, drawn by choosing where a borderless lump begins and ends. And the whole edifice rests on the claim that the clustering of those sparse beacons is too strong to be a coincidence. If that claim fails, if the clustering is a statistical fluke, or an artifact of how we collect the bursts, or several unrelated concentrations that only line up into one apparent wall from our particular vantage point, then there is no single coherent structure, and there is no tension with the cosmological principle at all, because there is nothing to be in tension with. The entire challenge to homogeneity evaporates the instant the structure dissolves back into chance and bias. The threat to the principle is real only if the wall is real, and whether the wall is real is the one thing we have never actually pinned down. So you can see now the strange and delicate position this candidate occupies. It is a tension, not a refutation. A puzzle, not a proof. If it is genuine, it presses against the scale at which the universe was supposed to smooth out, and against the time the universe has had to build things. And it would force cosmologists to think harder about how lumpy the larger scales are truly allowed to be. That would be a fascinating and significant development. The kind of thing that nudges a science forward by revealing that one of its convenient assumptions is more fragile than hoped. But it would still leave the great architecture of cosmology standing, repaired and refined rather than demolished. And all of that significance, every bit of it, hangs on a single thread that we have not yet tested, and that hangs in serious doubt. Whether the clustering of those explosions truly traces one connected thing, or whether the universe has merely arranged its scarce sparks into a pattern that our pattern-hungry minds have mistaken for a structure. It is worth dwelling for a moment on why this assumption, the cosmological principle, was ever adopted in the first place, because that history is what makes the tension feel weighty rather than trivial. The principle was not pulled from thin air. It was, in part, an act of humility, the natural descendant of a long demotion that ran through the whole history of astronomy. Once we thought the Earth was the center of everything, and we were wrong. Then we thought the sun was the center, and we were wrong. Then we thought our galaxy was the whole universe, and we were wrong. Again and again, every time humanity placed itself or its home at the center of the cosmos, the universe answered that we were not central at all, that our location was ordinary, that the view from here was the view from anywhere. The cosmological principle is the logical end of that long humbling. It says, let us finally stop assuming we occupy a special place, and let us build our cosmology on the assumption that the universe is the same everywhere and in every direction, because every time we have assumed otherwise, we have been embarrassed. The principle is, in a sense, the universe's repeated lesson encoded as a starting axiom. We are not special. Our spot is typical. The cosmos is democratic. And that is exactly why a genuine structure spanning a tenth of the observable universe would be so quietly disturbing. It would suggest that, on the very largest scales, the universe might not be as smooth and democratic as the long humbling led us to expect. It would suggest a return at the grandest level of features and concentrations and special regions of a cosmos that has not entirely surrendered its lumpiness, even at scales where surrender was promised. Not a violation of the deep principle that we are not special, but a complication of the simpler claim that everything averages out. It would mean the beach, viewed from standing height, is not perfectly smooth after all, that there is a faint ripple in the tan even when you back all the way up. And the universe would once again be telling us that one of our comfortable assumptions was a little too comfortable. That is the prize and the peril, riding on whether a few hundred explosions toward Hercules and Corona Borealis really do mark a single coherent wall. So we have laid the heart of the tension fully open now. We have seen what the cosmological principle actually claims, that the universe is homogeneous, the same in every place, and isotropic, the same in every direction. But only once you zoom out past the scale of homogeneity, a few 100 million light years, beyond which all the clumps were supposed to blur into smoothness. We have seen why a candidate 10 billion light years across collides with that promise, dwarfing the scale at which structure was meant to end, and straining even against the age of the universe and the patient slowness of gravity. And we have refused the easy drama, establishing instead the measured truth that one big structure does not by itself break a statistical principle, that even a real one would refine rather than destroy modern cosmology and would leave the Big Bang wholly intact, and that the whole tension exists only if the structure is a single, genuine, connected thing, which is exactly what remains unproven. Everything now funnels toward one final question. The question this entire story has been quietly bending toward from its first sentence. Is the wall a monster, or is it a mirage? Is the clustering a real concentration of matter, or a trick of sparse data, selection, and chance? That is the reckoning, and it is where we go now. So we arrive at the reckoning, the question that has been hiding inside every sentence of this story from the beginning. Is the wall a monster or a mirage? Is that clustering of explosions toward Hercules and Corona Borealis the fingerprint of a genuine, connected concentration of matter? The largest thing the universe has ever assembled? Or is it a ghost? A shape conjured out of sparse data, selective beacons, and the relentless human hunger to see patterns where none exist? Everything we have built points here. And the honest answer, the answer you deserve rather than the thrilling one, is that nobody knows for certain, and that the not knowing is itself the most important thing to understand. So let us take both possibilities with full seriousness, give each its strongest case, and feel exactly why this remains genuinely unsettled. Begin with the case against, because it is the more sobering and the more instructive, and because understanding why a structure might be illusory teaches you something deep about how science actually fails. The central danger, The one we've circled again and again is the marriage of sparse data and the pattern-hungry mind. Human brains are pattern detection engines refined over millions of years of evolution, and they are magnificent at it. So magnificent that they routinely find patterns that are not there. We see faces in clouds, animals in constellations, meaning in random noise. This is not a flaw we can simply decide to switch off. It runs beneath conscious thought. And when you hand a pattern-hungry mind a sparse scattering of points and ask it to find structure, it will find structure, whether or not any exists. This is precisely the situation with the gamma ray bursts, a few hundred points flung across a colossal three-dimensional volume, and somewhere in that thin haze, a region where they seem to crowd. The crucial question is not whether the crowding is visible. It plainly is. The question is whether crowding like that would show up anyway, by pure chance, even in a perfectly smooth universe with no structure at all. And here is the uncomfortable truth that drives the skeptical case. With few enough points, chance clustering is not the exception. It is the rule. Scatter a few hundred grains of sand at random across a vast table, and you will not get an even haze. You will get clumps, you will get bare patches, you will get somewhere a region where the grains pile up more thickly than anywhere else, purely because randomness is lumpy, not smooth. True randomness almost never looks even. It looks clustered, streaked, patchy, full of accidental concentrations that mean absolutely nothing. So when astronomers find a clustering of a few hundred bursts, the skeptic's first and entirely reasonable response is, of course you did. With that few points, you would expect to find some region of apparent clustering, even if the universe were perfectly uniform. The mere existence of a clump proves nothing. The only thing that could make the clump meaningful is if it is so dense, so far beyond what chance alone would typically produce, that randomness becomes an implausible explanation. And whether this particular clump clears that bar is exactly where the experts split. Then layer on the second danger, which is subtler and in some ways more corrosive than chance, the problem of selection. We do not see the universe cleanly. We see it through instruments from a particular vantage, with 1,000 quiet biases baked into how we collect our data, and every one of those biases can manufacture fake structure. Consider how gamma ray bursts are actually detected. They are caught by satellites watching the sky, and those satellites do not watch every direction with equal attention. Some patches of sky get more exposure than others, simply because of how the detectors are pointed and how they scan over time. This is called sky exposure bias, and its effect is insidious. If one region of the sky is monitored more thoroughly, more bursts will be detected there. Not because more bursts happen there, but because we are looking harder. And more detected bursts in a region looks exactly like a clustering of bursts in that region. The instrument's attention masquerades as cosmic structure. You think you have found a wall, and what you have actually found is the place where your telescope happened to stare longest. Now add a second selection effect, even more treacherous, sitting right in our own backyard. Our own galaxy, the Milky Way, is not transparent. It is full of gas and dust, especially thick along the band of the Milky Way that arcs across our sky. That dust absorbs and blocks light. So bursts that go off behind the thick dust lanes of our own galaxy are harder to catch. Their light dimmed or smothered before it reaches us, and harder still to follow up for the redshift measurement that gives them depth. This is called extinction bias, and it carves great swaths of the deep sky into shadow. regions where bursts are systematically underdetected, not because the universe is empty there, but because our own galaxy is standing in the way. And here is the poison in it. If bursts are suppressed in some directions by dust and exposure, then by simple contrast, they will appear over-concentrated in the directions that are clear and well watched. The clear regions will look clustered relative to the obscured ones, producing an apparent structure that is nothing but a map of where our own galaxy lets us see and where it does not. A skeptic looking at the candidate can argue with real force that what the bursts are tracing is not a distant wall of matter, but the near at hand pattern of our own dust and our own detectors' habits. And then comes the third and most statistically deadly of the criticisms, the one that has felled many a confident discovery across the history of science, the look elsewhere effect. Here is how it works, and why it is so easy to fall for. Suppose you go hunting through the sky for clustering. You do not test one specific spot that you chose in advance. You sweep across the whole sky, across the whole range of distances, asking everywhere, is there a clump here? Is there a clump here? Is there a clump here? You ask the question thousands of times in thousands of places. Now, even in a perfectly random universe, if you ask enough times in enough places, you will eventually stumble onto a region that looks startlingly clustered, just by chance. Because with thousands of trials, rare flukes become expected. They have to appear somewhere. And when you find that one striking region and calculate how unlikely it would be to arise by chance, you get an impressively small number. A number that screams significance. But that number is a lie because it ignores the thousands of other places you looked and did not find anything. You have been fooled by the breadth of your own search. The proper question is not, how unlikely is this one clump in isolation? But how unlikely is it that my entire skywide search would turn up at least one clump this striking somewhere? And that number is far, far less impressive. Critics of the candidate have pressed exactly this point. When you account honestly for how much sky was searched, they argue, the clustering toward Hercules and Corona Borealis may not be so extraordinary after all. It may be precisely the kind of fluke that any wide search of sparse data is expected to cough up. This is not hand-waving. It has been made carefully in the scientific literature. Researchers re-examining the burst data with different tools have reported that, under their methods, the clustering significance shrinks dramatically, that a perfectly isotropic universe with no structure at all could reproduce a clump as striking as this one a meaningful fraction of the time, well within the realm of ordinary chance. Others have argued that the apparent anisotropies in the burst distribution can be explained largely or entirely by the extinction and exposure biases we just described. That once you correct properly for where our galaxy and our instruments let us see, the structure fades toward nothing. And there is a final, almost philosophical blade in the skeptical hand, which is the very point about how separate things can masquerade as one. Even if there are real concentrations of bursts at that distance, there is no guarantee they form a single connected structure. They might be several genuinely distinct overdensities, ordinary clusters or modest superclusters that happen to fall at similar distances and similar directions, and that our crude, depth-blurred map smears together into one apparent giant. The depth measurements from redshift are not precise enough to cleanly separate structures stacked along the same line of sight. So a handful of unremarkable, perfectly allowed lumps could be averaging in our data into one impossible seeming wall. A wall that exists only in the blurring, not in the cosmos. Pull all of this together: the lumpiness of chance, the bias of exposure and dust, the trap of the wide search, and the smearing of separate things into one. And the skeptical conclusion is clear and strong. There may be no wall at all. There may only be the universe, smooth and democratic as the principle promised, dressed up by our limitations to look like a monster. But now we must turn, with equal honesty and equal force, to the case that the wall is real, because that case is not weak. And the scientists who built it are not naive. They have heard every one of these criticisms, and they have answered them, and their answers carry genuine weight. Begin with the simplest and most stubborn fact in their favor: the clustering did not go away. The original discovery rested on a relatively modest sample of bursts, and the natural expectation, if the clump were a mere fluke of small numbers, was that it would dissolve as more data arrived. Flukes are supposed to wash out, add more points, and a chance clustering should regress toward the smooth average, fading back into the noise it came from. That is the signature of an illusion, but that is not what happened. As the catalogue of bursts with measured distances grew, study after study, the clustering toward Hercules and Corona Borealis persisted. It did not vanish. By some analyses, it strengthened, with more and more of the deep sky's bursts appearing to participate in the concentration, the number of independently significant patches multiplying as the data deepened. A fluke that refuses to die as you feed it more data is a strange kind of fluke. The persistence of the signal across growing samples is the single strongest card in the proponent's hand, and it is not easily dismissed. Then, take the answer to the bias criticism, which is more sophisticated than the skeptics sometimes grant. The proponents are acutely aware that exposure and extinction can manufacture fake structure, and they have specifically designed parts of their analysis to be immune to exactly those effects. The key insight is this: sky exposure and dust extinction are biases in direction. They make certain patches the flat sky easier or harder to see, but they are not biases in distance. The dust in our galaxy does not care whether a burst lies at a redshift of 1 or a redshift of 2. It dims the near and the far in the same direction equally. So if you build your test cleverly, looking not just for clumping on the flat sky, but for clumping in depth, for an excess of bursts concentrated at one particular distance within a given direction, then a pure directional bias cannot fake it. A region that is merely well exposed or dust-free should show extra bursts at all distances along that line, not a pileup at one specific redshift. The candidate, the proponents argue, shows exactly the kind of depth localized concentration that directional biases cannot produce, a clumping that lives at a specific distance, which is the fingerprint of real structure rather than instrumental shadow. Whether this argument fully closes the door is itself debated, but it is a serious and pointed reply, and it means the bias criticism cannot simply be asserted. It has to be fought for. And then comes the strangest and most intriguing piece of the proponent's case, the one that lifts the whole question out of pure statistics and into theory. Recall the tension we built earlier in this journey. The idea that a structure this large strains against the scale of homogeneity and against the time the universe has had to build things. The natural reading of that tension is that it argues against the wall. that the structure is too big to be real and so probably is not. But there is a more unsettling possibility, and some theorists have leaned into it. What if the universe's true maximum structure size is larger than the simplest models assume? Independent theoretical work, pursued for entirely separate reasons, has explored the idea that there may be an effective scale set by the deep behavior of gravity over cosmic distances, beyond which structure changes character. And some of these calculations have arrived at a maximum scale that lands suspiciously close to the very size estimated for this candidate. That coincidence is provocative. It raises the possibility that the wall is not violating the rules at all, but revealing them. That it sits right at a genuine physical ceiling our simpler models had failed to anticipate. The proponents do not claim this proves anything. They are careful to present it as a possibility, a motivation, a reason to take the structure seriously rather than dismiss it. But it transforms the tension from a pure liability into something more interesting. A place where an anomalous observation and an unexpected piece of theory seem to be gesturing at the same number, which is exactly the kind of convergence that sometimes, not always, but sometimes, marks the early signs of a real discovery rather than a mistake. So weigh the two cases honestly, because that weighing is the whole point, and resist with everything the urge to declare a winner. On the skeptical side, sparse data clusters by chance, selection effects manufacture false structure, wide searches breed flukes, and separate lumps can smear into illusory giants, and careful reanalyses have found the signal consistent with a smooth universe. On the proponent's side, the clustering has stubbornly persisted and even strengthened as data grew. The analyses have been deliberately built to resist the most obvious biases, and a strand of independent theory hints that a structure of just this size might mark a real physical ceiling rather than a broken rule. Neither side has delivered a knockout. The skeptics cannot prove the structure is nothing, only that it could be nothing, that the data do not force you to believe in it. The proponents cannot prove the structure is real, only that it has survived the tests thrown at it so far and refuses to conveniently disappear. This is not a story with a resolved ending. It is a story caught in the genuine, unglamorous middle of science, where the claim is neither confirmed nor refuted, but simply, honestly, open. And that leads to the question that actually matters for the future. What would it take to settle this? Because a question being open is not the same as a question being unanswerable. The path forward is clear, even if walking it is hard, and it follows directly from the deepest weakness of the whole enterprise. The entire controversy exists because the structure was inferred from gamma ray bursts, which are rare, selective, and sparse. A few hundred fleeting beacons asked to map a tenth of the observable universe. The way to break the deadlock is to stop relying on the bursts alone and to look at that same patch of sky with completely different eyes, eyes that do not share the burst's weaknesses. If a genuine concentration of matter sits out there toward Hercules and Corona Borealis at that distance, then the bursts are not the only thing that should reveal it. The matter itself should be detectable by other means, and those other means are exactly what the field needs. Consider what an independent confirmation would actually look like. The most direct would be a galaxy survey, a deep and patient census of the ordinary galaxies in that exact region and at that exact distance. Galaxies are vastly more numerous than gamma ray bursts. Where a burst plants a single rare flag, A galaxy survey can count thousands upon thousands of points, and with that many points, the statistics transform. The lumpiness of chance that haunts a few hundred bursts largely dissolves when you have tens of thousands of galaxies, because real structure stands out clearly from random scatter once the sample is rich enough. If a survey of galaxies at that distance, in that direction, found a genuine overdensity, a region truly crowded with galaxies beyond the cosmic average, then the wall would graduate from a contested inference to a confirmed concentration. And if such a survey found nothing, just the ordinary smooth scatter of galaxies with no special crowding where the bursts had pointed, then the wall would be exposed as an artifact of the burst's limitations, and the tension with the cosmological principle would quietly evaporate. Either way, galaxies, by sheer force of numbers, could deliver a verdict the sparse bursts never can. It is worth slowing down on what such a galaxy survey actually involves, because the power of the method lives in details that are easy to skate past. To map structure in 3 dimensions, you do not just photograph galaxies on the flat sky, you must measure a redshift for each one, the same depth-giving stretch of light we have leaned on all along, and you must do it for not a few hundred objects, but for tens of thousands, hundreds of thousands, sometimes millions. This is a colossal undertaking. Each galaxy's light must be split into its spectrum and read for the telltale shift, and modern instruments do this by capturing the light of thousands of galaxies at once, night after night, year after year, slowly building a 3 dimensional atlas of the cosmos, one slice of sky at a time. The great surveys of recent decades, beginning with the Sloan Digital Sky Survey and continuing into ever more ambitious projects mapping tens of millions of galaxies and quasars, exist precisely to turn the flat dome of the sky into a navigable volume. And the crucial point is that for ordinary galaxies measured this way, the depth is far sharper than anything the sparse bursts can offer. This sharpness in depth is the very crux of the whole dispute, and it deserves to be named plainly. Recall the deepest weakness of the burst map, that its distances are crude, smeared, imprecise, so that separate concentrations stacked one behind another along the same line of sight can blur together into one apparent giant. The wall might be many things pretending to be one thing, and the burst data simply cannot resolve them apart. But a dense galaxy survey, with a precise redshift for every one of its myriad points, can slice the depth finely. It can ask, at this exact distance, in this exact direction, are the galaxies truly crowded? And then step a little nearer or a little farther and ask again, building a depth profile so detailed that a genuine single overdensity would stand out cleanly from a chance alignment of separate lumps, where the bursts give you a blurry smear in depth. A good galaxy survey gives you a series of sharp cross-sections, and it is in those cross-sections that the truth hides. If the crowding holds together across the depth slices as one connected concentration, the wall is real. If it dissolves into several distinct lumps at different distances that only overlapped in the burst's blurry view, the wall was an illusion of poor resolution all along. The sparse burst can never settle this. The dense, depth-sharp galaxy map can. And there is a deeper, more elegant tool that these great surveys carry, one that turns them into a direct test, not just of this candidate, but of the whole question of cosmic smoothness. It comes from a faint and beautiful relic of the universe's infancy. In the first few 100,000 years after the beginning, the cosmos was a hot, dense plasma, and through it rippled enormous sound waves, pressure waves sloshing through the primordial matter. When the universe cooled and those waves froze out, they left behind a preferred distance, a characteristic separation imprinted faintly into how matter is spread. A scale of roughly 4 to 500 million light years, at which galaxies are very slightly more likely to be found near one another. Astronomers call these frozen ripples the baryon acoustic oscillations, and they function as a kind of cosmic ruler, a standard length built into the universe itself by physics we understand well. By measuring this ruler in galaxy survey after galaxy survey, in patch after patch of sky, cosmologists have done something profound. They have confirmed again and again that the universe really does carry the same gentle imprint everywhere, that its large-scale statistical texture is consistent from place to place, exactly as the cosmological principle predicts. These surveys are, in effect, the strongest evidence we have that the universe genuinely does smooth toward homogeneity on large scales, that the principle our candidate seems to strain against is not an idle assumption, but a measured, repeatedly tested feature of reality. And that is precisely what makes the confrontation so sharp and so clean. On one side stands a candidate structure inferred from a few hundred rare, selective, depth-blurred explosions, hinting that the universe is lumpier on the grander scales than the principle allows. On the other side stand the great galaxy surveys, armed with millions of precisely placed points and a ruler frozen into the cosmos at the dawn of time, testifying that the universe smooths out just as expected. These are not vague philosophical positions. They are concrete, opposing measurements, and they can be brought into direct contact. Point the full machinery of a deep galaxy survey at that exact patch of ancient sky toward Hercules and Corona Borealis. Slice it finely in depth, measure whether the galaxies there truly crowd beyond the cosmic average, or whether they obey the same smooth statistics found everywhere else, and the candidate must finally declare itself. There is no hiding from a measurement that precise and that direct. The bursts open the question, but they can never close it. Only the dense, depth-sharp, ruler-bearing surveys of ordinary matter can walk up to that region of the deep past and report, plainly and independently, whether anyone is truly home or whether the wall was a phantom assembled from too little light. The instruments to do this are being built and turned toward the sky in our own era, mapping the deep universe in numbers that would have been unthinkable when the candidate was first proposed. The verdict the burst could not give is slowly coming within reach. There are other independent witnesses too. Quasars, the blazing cores of galaxies feeding supermassive black holes, are, like bursts, visible across enormous distances, but they are far more numerous and can be mapped in great quantity, offering another way to trace where matter clumps in the deep universe. A survey of quasars through that region could serve as a second independent check, agreeing or disagreeing with the burst-based claim. And subtler still, there is the technique of reading the gas itself through absorption lines. When the light of a distant bright object passes through intervening clouds of gas on its way to us, that gas imprints dark absorption features on the light, a barcode revealing the gas it crossed. By studying these absorption signatures along many lines of sight through the suspect region, astronomers can map the distribution of ordinary matter directly, not the rare star-forming flares it produces, but the gas itself, threading through space. A concentration of matter, if real, should leave its mark in that gas. A thickening detectable in the absorption barcodes of background light. Each of these methods, galaxies, quasars, gas, has different strengths and crucially different weaknesses. None of them shares the specific biases of gamma ray bursts, and that is exactly why they matter. The deepest principle in observational science is that a result you can only see one way, through one method with its own peculiar flaws, is a result you cannot fully trust. A result that shows up independently through several methods, each blind to the other's weaknesses, is a result that begins to compel belief. The wall will be confirmed or dissolved not by more bursts, but by these other eyes turning toward that patch of ancient sky and reporting whether anyone is home. And so we come to the end of the journey, honesty, with the structure still suspended in the very uncertainty it began in, which is, I think, a better and truer place to end than any tidy verdict could offer. Let us be clear about exactly what we know and what we do not, because that boundary is the real lesson here. We know, as a confirmed observation, that gamma ray bursts show an unusual clustering toward the constellations Hercules and Corona Borealis at a distance of roughly 10 billion light years. That clustering is a measured fact, re-examined many times. What we do not know, what remains genuinely unresolved, is what that clustering means. Whether those sparse, brilliant, selective beacons are flags planted in a single connected wall of matter, the largest coherent structure in the known universe, or whether they are a mirage assembled from chance, from the shadows of our own galaxy's dust, from the habits of our telescopes, and from the deep human tendency to bind scattered points into shapes. The candidate is not a confirmed object, and we have refused all along to call it one. Neither is it a debunked fantasy. It is a real and open question, sitting right at the frontier where our instruments run out of reach and our methods run out of certainty. What makes it worth all this time is not that it might be the biggest thing in existence, though it might. It is what it reveals about the act of knowing the universe at all. We are creatures on a small planet, trying to map a cosmos so vast that our brightest beacons number only in the hundreds, and our deepest looks reach back 10 billion years to light that left before the Earth was born. At those limits, the line between discovery and illusion grows thin, and humility becomes not a weakness, but the sharpest tool we have. The Hercules Corona Borealis Great Wall may turn out to be a monster that forces us to enlarge our picture of how lumpy the universe is allowed to be, refining a century-old assumption without ever toppling the science that rests beside it. Or it may turn out to be a mirage that teaches us, yet again, how easily sparse data and eager minds conspire to see walls in the dark. We do not yet know which. And the willingness to say that plainly, to hold the question open until the galaxies and the quasars and the gas have had their say, is not the failure of the story. It is the whole of it. Somewhere out there, 10 billion years in the past, the brightest deaths in the universe are still clustering on our maps, still refusing to tell us whether they are tracing the grandest architecture ever built or simply the shape of our own not yet perfect sight. And until we look again with better eyes, the wall waits in that uncertainty, neither monster nor mirage, but the most honest thing of all, a question we have not yet earned the right to answer.